Hi there. In this video, we'll look at a problem from lesson 4.2. This was taken from the homework set on page 202, problem 16. And the directions indicate that we are to use analytic methods to find the local extrema and the intervals on which the function is increasing, as well as the intervals on which the function is decreasing. Okay, so general strategy for this is to find the derivative. Which makes sense, knowing that the whole chapter is really about applications of derivatives. We should expect that that might come into play. Two, we'll find each critical point, and we'll use the slope. We'll use those critical points to determine where the slope of the graph is positive and where that slope is negative. And once we know that, we can then draw a conclusion about where the graph itself is increasing or decreasing. As usual, before we jump in and start using calculus, we should see what we can learn about this function in general using just things that we learned in Algebra 1, Algebra 2, and pre-calculus. So let's spend just a couple of minutes making some observations about this function. So first of all, we know that this is going to be a parabola of some sort, and it's easy enough to find the zeros in this case. And we can make that easy by factoring the expression. So this looks like x minus 4 times x plus 3 will equal g of x. And if we want to know where this is equal to 0, that's easy enough to do. You can tell that g of x is 0 when x is 4. So when the input is 4, the output is 0. And when x is negative 3, we also expect the output to be 0. All right, so negative 3 should be a 0 for this function, and 4 should be a 0 for this function. And we expect it to be a parabola that faces up, so perhaps it looks something like this, and there you have it. Real rough general sketch just from the zeros. Okay, another general question that we like to ask about functions is about their end behavior. What happens if we use a large input, large positive numbers, large negative numbers? And we know in general a polynomial at its ends behaves like the term that has the largest power. So if we can analyze the end behavior of x squared, then we know something about the end behavior of g of x. And we know that for large numbers, when you square them, you get a positive answer. And for large negative numbers, when you square them, you get a positive answer. So that's what we expect in terms of end behavior, which happens to agree with our analysis here. Okay, so far so good. We've looked at zeros and end behavior. Last thing for parabolas, it's so easy to find the vertex, we might as well just do it using the methods of algebra. Again, we determined that the zeros are negative 3 and 4, and we know that parabolas are symmetrical graphs. So therefore, the number that's halfway between these two zeros, let me just do the math here, halfway between 4 and negative 3 is 1/2. So right there, I know that this should be the line of symmetry for this function. And if we actually plug that value in, we should be able to get the vertex. G of half equals some number. And if we knew that what that number was, I won't take the time to compute it, but that would give us the vertex. And then we have a very clear picture of what the graph looks like from there. And in fact, we should be able to use that to determine that the graph is decreasing up to the vertex and is increasing away from the vertex. Okay, so we can actually answer this question without any calculus at all, but just in order to practice the techniques, and hopefully also calculus works, so we should get the same answers whether you use algebra or calculus. Let's go ahead and do that. So step 1, we'll compute the derivative. G prime is 2x minus 1. Step 2, the critical points occur when the slope is 0 or undefined. And evidently, that happens when x is 1/2. So this function has exactly one critical number, which is 1/2. And that, just notice that agrees with this analysis right here, which says that the vertex is halfway between the two zeros. So far, so good. That's making sense. Calculus is working so far. And as we continue, we'll take that critical number, which is 1/2, and we'll place it on a number line. And step 3, we'd like to know where the slope of the graph, so where is g prime positive and where is g prime negative? Well, we know in particular g prime is 0 at this critical number. And so let's go ahead and choose a value to the right of 1/2, like 5. And let's go ahead and plug that into the formula for the slope. And we get 10 minus 1, which is 9. 9 is a positive number. So that tells us if you choose any value larger than 0, you should expect for the slope to produce a positive answer. Okay? And over here, let's choose a value less than 1/2. Oh, how about 0? And you get 0 minus 1, that's a negative number. And that tells me if I pick any number less than 1/2, the slope formula will produce a negative number. Okay, so let's put this off to the side here. We're done with that. Okay, and from this, we can now draw a conclusion about the behavior of g of x, the outputs of the function. Okay, so we're using information about slopes to make some inferences about outputs. All right, if the slope is negative, we're picturing the graph doing this. And if the slope is positive, we're picturing the graph doing this. Okay, in particular, when the slope is negative, whoops, the function is decreasing. Can I back that up? When the slope is negative, the function is decreasing. When the slope is positive, the function is increasing. And when the slope is 0, apparently it has this local minimum. Okay, and yet again, let's go back and compare. Isn't that what we thought the whole time? Just by using algebra and general common sense. And again, calculus is working out in the way that we would expect. Okay, so let's pull everything together and write up our answers to this problem. So, we found that the function has a critical number where x is 1/2. It is 0. The output is 0 for -3 and 4. And can we go ahead and plug in 1/2 and see what that gives? Okay, 1/2 squared is 1/4. And 1/4 minus 1/2 is -1/4. Oops. 1/4 minus 1/2 is -1/4. And so we get -12 1/4. All right, so now we know what that value is, -12 1/4. It's off the chart, way down here somewhere. And then we're going to see the graph rise up to the 0, and behavior goes up here. It'll rise up to the 0 this way, and behavior goes up here. And there is a nice accurate picture of our graph. And now to write up the answers. So this happens to be a local minimum. In fact, it's the absolute minimum. And we get f of x equals 12 1/4. And that particular minimum value occurs when x is 1/2. So there we've answered part A. Okay, and the first derivative test comes into play because the slope changes from negative to positive. Okay, next. The outputs of the function are increasing when the graph rises from left to right. And that's happening for these values of x to the right of 1/2. So let's write when you're at 1/2 all the way to infinity, the graph's going to rise. Okay, now let's look at part C. Whoops, the graph is decreasing when it falls from left to right, which happens here, and that's happening for the inputs to the left of 1/2. Okay, so let's state that as an interval from -infinity all the way up to 1/2, the graph is dropping. Okay, and there you have it. We've answered all three parts of the question, and we've seen that calculus agrees with what our algebra and common sense view of the function tells us, and so all is well. Thanks for watching. Hope you found that helpful. See you next time.